you'd probably be aware, particularly from the video, Arman's from Iran. He completed his undergraduate degree there in mechanical engineering, manufacturing and production.
Yep.
Yeah. And then he did his master's in Sweden on waste disposal.
Waste treatment.
Waste treatment, yeah, waste treatment. And then he joined us here at UNSW to study his PhD, and you'll hear all about some of the work that he did during his PhD during the talk. Arman tells me that his thesis now is all approved and everything, so he becomes my 64th PhD student to complete, and the number 2 from Iran.
Yep.
So please. Arman.
Thank you so much. Thanks so much, Professor Green, for the introduction, for the kind introduction. And thanks to all of my supervisors for all their support. I have an acknowledgement list at the end of my talk. Okay, I'm going to talk about optoelectronic characterization of perovskite, thin films, and solar cells, what I did during my PhD here at SPREE. I'm going to briefly introduce I'm going to briefly introduce the organic inorganic metal halide perovskites, which are used in optoelectronic devices. Then talk about the development of luminescence imaging technique here, and I will focus on the investigation of light stability of perovskite solar cells. Then I will present some results on the excitonic characteristics of perovskites. By this, I mean the excitonic binding energy and reduced mass of these materials. And we'll look at the impact of a microstructure on these parameters, and I briefly talk about polaronic effect in these materials. Perovskites. Organic inorganic perovskites are crystallized from organic and inorganic salts into a perovskite structure. You can see a cubic structure here. The general formula is ABX3. A is usually a monovalent cation. Commonly, methylammonium, formamidinium are used, and more recently, cesium and rubidium are used as the A element. And you can see A is located in this cuboctahedral space in the perovskite structure. B is the divalent cation, lead or tin can be used, and X is the halide. Perovskites have been used for the fabrication of photodetectors and light-emitting diodes, but what we are all interested in is their application in photovoltaics. They have quite a lot of pros. I've put 4 of them here. One is that you can fabricate perovskites with different composition, and as a result, you will have materials with different band gaps. You can see here in this plot that the band gaps can range from near infrared to UV, and the efficiencies delivered so far using these compositions are quite a wide range. Then they have quite a high absorption coefficient in the order of 10 to the power 4 to 10 to the power 5 in the spectral range of interest, comparable to other direct band gap semiconductors. They're usually considered as direct during absorption process, but recently direct indirect there has been shown that the characteristics of the band gap is direct indirect during the recombination process. They have quite long charge carrier diffusion lengths. Most recently, single crystals have been fabricated with more than 175 micrometer diffusion lengths, and this is just a photo of that single crystal reported in the literature. They have low excitonic binding energy that I'm going to talk about today. They have some issues as well. One, although might sound surprising, but they have quite high non-additive recombination losses in these materials, and people are working on addressing this issue. Just to give you an idea, the defect density has been reported to be in the order of 10 to the power 15 to 10 to the power 17 per centimeter, cubic centimeter in the polycrystalline perovskites. You can compare that to the CIGS semiconductor in the order of 10 to the power 13, and also single crystals are within the region of 10 to the power 9 to 10 to the power 12. They have the stability problem that can be due to the long illumination, can be happen at high temperatures, also in a humid environment, and also due to the oxygen diffusion into the perovskite. For instance, here I've just presented, I want to show you the metal ammonium lead iodide, the typical perovskite composition that is used, that when you heat it at 150 degrees C for 60 minutes, this one degrades into lead iodide in air, while when you replace the metal ammonium with Fa, you have quite a stable thin film. Also, photocurrent hysteresis occurs in these materials and the devices fabricated from the perovskites. By this, I mean by changing the voltage range that you measure the IV, by changing the voltage sweep rate and also sweep direction, you might end up with different IV curves, as you can see here. By changing the sweep rate, you'll have different IV, and also by changing the direction, choosing the different direction, also the IV curve changes. Anyhow, they have very a lot of good properties, electrical properties, that resulted in a dramatic increase in their efficiency since 2012, when the first solid-state perovskite device was fabricated with efficiency around 9, and now efficiency is more than 22% has been reported. Okay, what I'm going to talk about, which covers part of my PhD, is the luminescence imaging technique. Photoluminescence and electroluminescence imaging has been serving the silicon PV community very well, both in research and development and also at industrial level. You can see here just example of crystalline silicon solar cell. With this left-hand side column is the PL image. In the middle you see EL image, example of EL images. And if you manipulate the images, you do proper calculation, you can spatially resolve the electrical properties. For instance, at the right-hand side, you can see series resistance maps. Then Ziv and I, we teamed up to be the first group to use the luminescence imaging technique on perovskite solar cells. And I ensure you that the light intensity in the background is lower than the safety limit. During my PhD, we first looked into the validation of Planck's generalized emission law, and then investigated the impact of pretreatment on that, on this emission law, and then I look into the dark degradation of the solar cells. But what I'm going to focus on today is the application of luminescence imaging on the effect of prolonged illumination, both immediate effect and also the long-term effect. Okay, here you can see a typical luminescence imaging setup. For doing the photoluminescence imaging, you need a light source. This is an LED, illuminates the device. You create the carriers, they recombine. The radiative recombination is detected by a CCD camera. If you want to do electroluminescence imaging, we just bias the device, and then the injected carriers recombine, and we detect the photons. Different imaging measurements that I'm going to present is PL at open circuit condition, PL at short circuit, and EL at different terminal biases. Okay, the devices that I used in all the studies are planar structure perovskite solar cells with methyl ammonium lead iodide as the active layer, the perovskite layer, compact titanium as the electron selective contact, and sparo as the hole selective contact. The device active area, which is the gold deposited area, is around 8 by 8 millimeter. And you can see here a schematic of the device. It's a super straight device, and you have the FTO, titanium, perovskite, the sparo, and the gold. And all the devices are epoxy edge sealed, so they are encapsulated. This is a photo of a typical device. You're looking at from this side, where you have gold, and this dark brown is the perovskite layer. For all the IV measurements, I've used a mask. The mask has a diameter of 4.5, and you can see this here circular aperture of 4.5 diameter. Okay, so in order to look at the effect of prolonged illumination on these devices, I performed several IV scans. It's very common among researchers in perovskite field that they do several scans and then report the efficiency. even in the very high efficiency cells. So here you can see an EL image of a pristine device, so nothing has been done on this device, no preconditioning, anything. Then I perform several IV scans. Each scan takes around 45 seconds. Right immediately after doing the IV scan, I realized that there is a fingerprint of the circular aperture of the mask left on the EL image of the device. And this is a good way to track the fate of this bright area, right? And this bright area, which is enhanced EL, is the region that we have illuminated, and the surrounding is where it was masked. So no illumination, this area. So this region has been masked. So in this EL ratio image, you can see a clear effect of illumination, where you have enhanced EL intensity. So EL intensity is proportional to the photovoltaic external quantum efficiency, and also exponentially proportional to the junction voltage. The EQE actually reflects the quality of the active layer, the perovskite here. For instance, the diffusion lengths of the charge carriers and the recombination rates. And the junction is mainly affected by the series resistance. So here, the reason for increased EL intensity can be twofold. One is that we have sort of annihilated the defects, and the effective lifetimes of the carriers have improved in the perovskite, or the bulk and interfacial series resistance in the device in this region has been reduced. So it's easier for the carrier to be injected into the device. In order to understand the effect better, I perform PL at open circuit condition as well. This is an image of the pristine device, and then PL image right after the IV measurements. And you can see here that the region which was illuminated appears darker with respect to the surrounding, which was masked during the IV measurement. And this is a clear picture of that effect. You can see that this region, the effective lifetime of the carriers, has reduced. Okay, again, PL at open circuit condition, what it tells us that we have the non-additive recombination increase either at the front interface, which is the perovskite and the titanium. I showed you in the schematic that we illuminate the device from the glass, and the first layer is the titanium. Or the non-additive recombination has increased in the bulk. Again, can be both together. But in the EL, we interpreted EL as increased lifetime of the carriers. So we probably are seeing an increased non-additive recombination at the front surface. To better understand this effect, I use another device, performed IV measurement, and this effect is regardless of the direction of the measurement, direction of the IV measurement. And then perform PL at short circuit condition. You can see here in the PL at short circuit condition, the region which was illuminated appears darker than the surrounding, which was masked during the measurement. This anti-correlation between EL and PL at short circuit condition, it suggests us that the series resistance has reduced in this region. So it's easier to extract carriers after the IV measurement in this region. So the concentration of carriers in the perovskite is lower, and the PL appears darker. The other reason could be that we have increased the non-additive recombination at the rare interface, which is the perovskite and the spiro. To clarify this effect, to have a better understanding of this effect, I used the bilayers, the perovskite and the spiro, and the titanium and the perovskite. For the perovskite and the spiro, I illuminated from the perovskite layer side, and also this one from the titanium side. These are the pristine layers, so no measurement has been done on these. And I light soak these because we don't have the full device, so we can only light soak it, and also we can only do PL measurement, PL at open state condition measurement on these. So after the light soaking, we realized that the region which was illuminated appears brighter than the surrounding. And this tells us that the bulk quality has been improved. So we cannot, the previous observation cannot be attributed to the increased non-additive recombination in the bulk or the back interface, the rear interface. And then I performed the light soaking on the titanium and perovskite bilayer and realized that after light soaking, the region which was illuminated appears much darker than the surrounding region. This tells us that the front interface is causing all these effects. And most likely, the non-additive recombination is increasing in this front surface between the interface between the titanium and perovskite, and reducing the effective lifetime of the carriers. And usually, these defects are probably formed in few atomic layers close to the interface, and usually they're not picked up with XRD to see if there any decomposition or degradation of the material is happening. And now, so far, the immediate observations after prolonged illumination are the improved series resistance. By this, I mean reduced series resistance in the region which was illuminated. The bulk non-additive recombination possibly reduced. I showed you in the bilayer of the perovskite and the spiral. And also the front surface non-additive recombination has increased. Again, in the previous slide, we saw that in the PL images of the titanium and perovskite bilayer, and possibly the back surface non-additive recombination has increased, but this needs to be investigated more. Then I want to see what is the long-term effect of prolonged illumination on the perovskite devices. So I took another device, performed several IV scans, and right after IV, you can see again the region which was illuminated appears brighter, and this AA is the aperture area, and this region is the surrounding. Then I tracked the EL images. So during the EL imaging, I stored the device in dark in glove box, so it's a oxygen-free and moisture-free environment. So we look at the EL images over time, about 2 weeks. We can see after 1 day, still you can see some highlights of the illuminated region with higher EL intensity than the surrounding. But over time, you see that the region which was initially very bright becomes much darker than the surrounding. OK, you can see here that the region we illuminated, the AA, the aperture area, showed a dramatic increase in EL intensity right after IV measurement, and over time showed a very fast decrease in EL intensity, while the surrounding, which is only affected by the cyclic voltage during the IV measurement, shows degradation with slower pace. So we have a device, we illuminate a region locally, and we see that the EL intensity in that region improves right after the prolonged illumination, and the PL at open circuit condition drops. Over time, we see that the region which had higher EL intensity shows a faster degradation in EL. EL, it's a very strong technique to give us information about series resistance by itself. Yeah, there are techniques that you use few EL images and roughly get a series resistant image. So this tells us that initially we have low series resistance. As a result, we have high EL intensity, but over time we have increased series resistance and lower EL intensity. And I showed you that it's most likely the front surface, the perovskite and titanium. So what is happening here is probably that the interface is degrading, and the series resistance is increasing, and EL is dropping. Then I perform also PL at open circuit condition to see what is happening to the bulk of this material over time. A PL at open circuit condition, interestingly, shows a higher intensity in the region which was illuminated compared to the surrounding over time, after 2 weeks. You can see it here. The line scan intensity is plotted here. You see the region which shows low EL intensity shows high PL intensity, right? So there is anti-correlation between the EL and PL at open circuit condition. Initially, you have high EL in the illuminated region, low PL. Over time, you have low EL and high PL, right? So soon, I will show you that I claim that there is an electrical or physical decoupling happening over time at the interface between the titanium and the perovskite. That is why we see higher PL intensity, while because there's a decoupling happening at that interface, your series resistance increases, and as a result, your EL intensity drops. I took another device. This time I light soak it only for 30 minutes. You can clearly see again the improved EL intensity right after light soaking, but after 1 day, I realized that the region which was illuminated has a very low EL intensity. Again, this is consistent with the previous results. However, it happened faster. The degradation happened faster, probably because the illumination was longer. The time of the illumination was longer, right? Then I performed PL at open circuit condition on the device again after 1 day. I realized that the region which was illuminated has a higher PL intensity compared to the surrounding which was masked, right? Okay, so I argue that there is electrical decoupling happening between perovskite and titanium after prolonged illumination over time. So there is a detachment happening. Your series resistance increases, and your PL also increases. So your series resistance increases, your EL intensity drops, and also your PL intensity increases. Look at this plot. This shows you the occurrence and frequencies of the PL intensity of a neat methyl ammonium lead iodide film, only the film, and you can see that the peak intensity of the PL for the film is around 1 order of magnitude larger than the film in contact with the titanium or in contact with the methyl ammonium. So you have a pure film, has a very high PL intensity. When you make the flat junction with the contacts, the PL intensity drops, probably because you form a lot of defects at the interface. So the region that we have lost the contact, the PL is high because we have the perovskite emitting. It's not in touch with the titanium. Could be just electrically, or could be physically. But in the surrounding, you have the junction, so the PL is quenched. I also perform XRD after 50 days just to make sure that during the illumination and also storage, the perovskite is not decomposed into the products like lead iodide, and usually lead iodide appears at the 12.5 angle of 12.5, and we don't see that here. And we also did TEM, cross-sectional TEM, and we realized that in the region which was illuminated, most of the time, during the preparation, the device is separated at the contact close to the titanium, right? The perovskite is broken or damaged close to the titanium. While for an intact device, for a pristine device, we didn't experience that. Okay, I tried to briefly explain the mechanism underlying these effects. Here you can see the evolution of the luminescence intensity ratio for a device. For the EL, I showed initially it has when you fabricate a device, you have an EL intensity, and then when you illuminate the region, EL intensity increases over time, drops. The PL shows anti-correlation. After illumination drops and over time increases. The PL at short circuit condition, I showed that after illumination drops, but we predict that increases over time because when you lose the contact, the carriers cannot be extracted during short circuit condition measurement. They recombine and you have higher PL intensity. Okay, when you have a pristine device in dark, the built-in electric field, in perovskites, it's very well known that they have ionic migration. So when you have the device in dark, the electric field, the built-in field, actually causes the ions to move to the corresponding contacts. And negative ions move to the titanium side, accumulate there, assuming that you have a fixed charge concentration. They actually narrow the Debye layer and increase the band bending and increase the electric field. The same happens at the spiro side. This is in the dark. Right after illumination, you have a negative field at the central part of the device in the perovskite because you don't give the ions enough time to move away from the contacts. But over time, they diffuse the photovoltage induced by the generation of the carriers upon illumination. It causes the ions to diffuse away from the contacts over time. And as a result, you have a lower electric field at the interface, assuming that you have similar amount of charge as in the dark. At lower electric field, your series resistance is reduced. That's why right after prolonged illumination, you have higher EL intensity. Yeah, I have explained this by ion migration. I show you initially that this is a perovskite structure. You have methyl ammonium in this cubooctahedral space. When you illuminate it, when you bias the device, the organic cation, the methyl ammonium can move out. It can distort the perovskite. Perovskite is a very soft ionic solid, at least the methyl ammonium lead iodide. And also the iodine defects can also move around. That breaks the bonds. So I believe that when you do the prolonged illumination, the ions move away from the contact, and then again when you rest the device, they want to recover, and all of these back and forth processes weakens the structure. And when you do, for instance, TEM, it separates at that interface, and over time actually you lose the contact. So I hope that you have been convinced that the interfacial decoupling happening happens at the titanium and the methyl ammonium lead iodide perovskite upon prolonged illumination over time. And then this has an important implication on credible stability investigation of these devices, because if you measure the IV on one part and then condition the device and want to come back and again measure the IV, you need to measure the same spot. Otherwise, you're measuring different spot, which is over time affected like differently. So it's very important to measure the same spot. Also, we have explained these all these mechanism thoroughly in this paper via ionic transport in the perovskite layer. Also, I'm going to move to another topic and discuss this for about 10 minutes, 15 minutes, which is excitons in polar semiconductors such as perovskites. What is exciton? When you excite an electron in a semiconductor, which is sitting in the valence band, excited to the conduction band, for instance by illumination, it leaves behind hole, which is the absence of electron. The electron has negative charge, hole has positive charge. They interact through the Coulombic forces. Assuming effective mass approximation, you end up in a hydrogen-like system where you have an electron going around a proton, right? And I'm sure that you remember 13.6 eV is the ground state energy of a hydrogen atom. And if you want to get the binding energy in a hydrogen-like system, like perovskites, you need the reduced mass, and also you need the dielectric constant of the medium to get the binding energy. And they scale, and the energy of the excitonic transition scale with respect to the band gap through this equation by this term, and n is the quantum number of the excitons. Also polaron. In polar semiconductors, semiconductors that have at least partially ionic bonding, when you introduce a carrier into the lattice, it polarizes the lattice. It means that it interacts with the positive and negative atoms. For instance, an electron attracts a positive atom, repels a negative atom, right? And this polarization of the lattice surrounding the carrier can be described by a phonon cloud, mainly longitudinal optical phonons, LO phonons. And the entity of the electron and this phonon cloud is called polaron. Okay, why excitonic binding energy and reduced mass are important? The knowledge of exciton binding energy can tell us about the majority of the photogenerated carriers, whether free carriers or they're excitons. Do we need to modify the design of the device so we can separate the excitons, such as what we do in OPV, for instance, bulk heterojunction, which one reason is to separate the excitons quickly. Also, it can affect your peer response. And also, the knowledge of excitonic reduced mass is important in the determination of the charge carrier mobility, which is proportional, inversely proportional with the reduced mass. Okay. There are different ways to fabricate perovskite layers. You can change the concentration of the precursor, you can change the annealing time, annealing temperature, you can change the substrate, and you end up with different morphology of the film. You end up with different microstructure, you end up with different grain size and grain and the crystal quality. So it was interesting to find out whether that affects the excitonic properties of the perovskites. So we fabricated 4 different morphologies: large polycrystalline perovskite, small polycrystalline, single crystals, small single crystals, and also perovskite infiltrated into mesoporous aluminum oxide. These are all methylammonium, the conventional perovskite composition, methylammonium lead iodide. Then, just to make sure that we've got the perovskite structure, we perform XRD. You can see these are the main signatures of perovskite structure formation at room temperature. In the small polycrystalline sample, we can see here that there's a small hump at the angle of 12.5, which indicates that there is a small residue of the lead iodide in the sample. Also, more in the single crystal. It depends on the technique that you use to fabricate the film. Okay, in order to characterize the excitonic properties, we use a technique which directly gives you information about these 2 parameters: excitonic reduced mass and binding energy. And it's called the magneto-optical measurements. You perform the typical transmission measurements under magnetic field. You change the magnetic field and look at the change in the optical response of the sample. Here you can see a typical transmission spectrum of the large polycrystalline sample. And this strong dip is the 1s state of the hydrogen-like system in perovskites, which blue shifts with increasing the magnetic field. Then at the higher energy, you have a shoulder, which is the 2s state. Then in order to resolve all the small features in the spectrum, we took the ratio of the transmission at a specific magnetic field to the transmission in the absence of magnetic field. You can see in the inset that this dip is associated with this 1s state, and the other dip at the higher energies is the 2s state. When we look at the higher energies, we see more dips in the spectrum. And these are associated with the free carrier transition states. When you put a sample in magnetic field, the excitons, the movement of the excitons in the plane perpendicular to the magnetic field is quantized. So the movement of the free carrier is quantized. Normally, in the absence of any external field, the transition states are continuum for free carriers. But under magnetic field, they quantize. And they're called Landau levels. These are explained by the Landau level transition energies are explained by this equation. N is the quantum number of the Landau level. B is the magnetic field, and this is the reduced mass of the exciton. Okay, if we plot these transition energies as a function of magnetic field, so all these Landau levels which happen at high energies, you plot that as a function of magnetic field, and you fit it with these independent of the exciton binding energy and independent of these excitonic transition states, you can extract the reduced mass, because reduced mass is this one and the band gap is the only free parameters. You fit it, you extract the reduced mass. And it's this one. This is for the large Polaronic crystallines. Then, and also the theory for excitonic transitions under high magnetic fields is also developed by Makado, and thorough explanation of that is given in this paper. I'm not going to go through that. But then you fix the reduced mass and fit the data for the excitonic transitions, and then you extract the binding energy directly. Here you can see a plot showing the overlay data, both excitonic and free carrier transition energies for all 4 samples. You can see that they're nicely overlaid, which means that the optical response of all these 4 samples under magnetic field is similar. And the extracted values for the binding energy and also the reduced mass, you can see they're almost unchanged, right? And you can see here, by change the crystal size, which also is probably crystal quality, the binding energy and the reduced effective mass will remain almost constant. Okay, we wanted to generalize this finding. We needed to fabricate samples, state-of-the-art sample. One of them is the triple cation lead mixed halide perovskite, which gives efficiency. Devices fabricated from this composition give efficiencies more than 22%. So we fabricate 2 morphology of this composition, a planar sample and also a mesoporous sample, where this material is infiltrated into the mesoporous aluminum oxide scaffold. We perform the same measurements, and you can see here that the binding energy and the reduced mass for the 2 samples remain unchanged. Okay, I didn't talk about polarons, but I will briefly talk about that in this slide. As I showed before, the effective Rydberg, which is the exciton binding energy, is proportional with the reduced mass and inversely proportional with the square of the dielectric constant. When we do these optical measurements, like these magneto-optical measurements, what we extract is the polaronic reduced mass, right? The theory of polaron was which is the transport of an electron in the lattice vibrational field of the lattice vibrations, was developed by Frohlich. And he came up with this alpha, which is the coupling constants between the electron and the phonons surrounding it. And then Feynman further developed this theory and said, okay, the polaronic mass is something larger than the rigid mass. And this is because of this coupling factor, which is inversely proportional with the square root of the phonon energy, right? So the polaron mass is larger than rigid mass that you calculate from the band structure, electronic band structure of the semiconductors. And I just want to show you a picture that you always remember what is polaron, is that a free charge wants to move around on the scene or in the lattice, but the phonons are grabbing the charge carrier, doesn't let it move. And this polaronic effect is one of the reasons that the charge carrier mobility in perovskite is limited when you compare it to, for instance, gallium arsenide. Anyhow, I hope that I have convinced you. So the binding energy that I showed you was around 13, 16, and all these measurements were performed at 2 Kelvin, right? So 16, 13 at 2 Kelvin. When you go to room temperature, the thermal energy is around 26. So easily the excitons can be dissociated into free carriers upon formation, upon illuminating the semiconductor, right? So they truly play a negligible role in the operation of perovskite solar cells, regardless of the fabrication technique, the morphology, the microstructure of the perovskite layer. Here I present like some universal values for these parameters. And another important outcome of our study was that the inorganic cage here, lead iodide, is likely to have the greatest contribution to the excitonic characteristics. This was another important result of our study that you can, again, read more about that in the paper. At the end, I have to thank my lovely family who have always supported me through life, unconditional love and support, and my parents who have been always my inspiration. Whatever I did, I owe them. Yeah, thanks to them for all the great support and love. I have to thank Professor Richard Korkish, because I'm at UNSW because of him. It has a long story, but I'm here because of him. Thanks Professor Green and also Professor Kanibier for all their support throughout my PhD, Dr. Hobaili, and also Dr. Taibji for kind support, and all my good friends and colleagues at UNSW. Thank you so much for your attention.
Thank you, Arman. Any questions?
So, perovskite, what you studied is about the photovoltaic, right?
Yeah.
So we saw some degradation when it's being exposed to light.
Yeah.
So do you have any idea about, because if it's photovoltaic, it should be exposed to light,
Yeah.
and it's going to degrade, so it will be pointless. Any idea about any solution or any proposal about it?
Firstly, proper encapsulation can improve the stability of these devices. One of the reasons of degradation is the interaction of the light and oxygen in the perovskite layer. And proper encapsulation, it prevents the oxygen to go through.
So you think oxygen diffuse into your structure?
Can be, because our technique is one of the very simple techniques for encapsulation, which is epoxy edge sealed. My colleague here has developed a technique which is much better than this. So if the encapsulation technique is improved, you probably can get more stable devices. And also the composition. So this study was done on the archetypical perovskite composition, which is methylammonium lead iodide. If you make different compositions with different cations and halides, you get more stable devices. And currently, 1-year stable devices has been reported in perovskite by incorporating some 2D perovskites into the 3D perovskite. Yeah. Yep.
Thanks very much, Arman. It was very interesting. Did you try any series resistance imaging for your PL images?
That's a very good question. I had this idea like since more than 1 year ago, but there is one big problem with perovskite, and that is the transient behavior of their electrical properties, right? Even in very high efficiency cells. I'm right now preparing a manuscript about this, how you can quantitatively interpret the results while having these transient effects. So when you bias the device, for instance, let's say we want to do EL imaging and extract the series resistance image. While you bias the device, the EL intensity starts to rise, saturates, and then degrades, even in very high efficiency cells. So this is an issue because you don't know, because for instance, you need 2 different biases, and then manipulate the images and extract the series resistance, right? That's one way to do it. But in that case, you don't know at which timing you should collect the image, so you can match the two images at two different voltage biases. That's an issue. That's why it's not really, I don't know if it is reliable to report that at this point, if the luminescence behavior is not stable. Yeah, but I have that in mind to do that. Yeah.
Okay, if there's no more questions, I think we should all thank Arman again for what was a very excellent talk. Thank you.
Thanks so much.